a pleasure to have here Chiara Toldo from Brussels and Milan also.
For now.
Okay. And talking about the thermodynamics of black holes near extremality, please.
Okay, thank you very much for the invitation. So it's a pleasure to come here and talk about black holes near extremality. I will focus mostly on Kerr black holes and on de Sitter black holes. All of this is work based on collaboration with these wonderful people. Really happy to have them as my collaborators. And I'm also very happy to report that I talked first about near extremal black holes in de Sitter, really here at this workshop 2 years ago. And I was pleasantly surprised that even now, Giulio and Alessandro started working on de Sitter black holes. Cannot claim credit for that. But okay, so let me just start with a bit of an introduction, since the audience is a bit mixed. So indeed, so black holes are very important objects in theoretical physics. There is a very nice and striking correspondence between laws of black hole mechanics and laws of thermodynamics that dates back even 50 years. So indeed, this law here, satisfied by black holes, it really resembles the second law of thermodynamics here that led indeed Bekenstein to associate an entropy proportional to the event horizon to black holes. And also, like after taking into account quantum effects, Hawking showed that indeed black holes radiate at a purely thermal spectrum, which is indeed like they radiate at a temperature proportional to the surface gravity kappa. So this like correspondence is not just an analogy, but really a lesson that drove a lot of progress in quantum gravity for the past decades. So indeed, the fact that black hole entropy scales as an area rather than the volume, indeed was one of the inspiration for the holographic principle and then for ADS-CFT, and so on and so forth. But so black holes have really entropy. And indeed, if you compute the entropy for a black hole, for instance, that exists in our universe, you get really a huge number. So black holes have huge entropy. However, in general relativity, they're rather simple objects. So indeed, they're specified by just a few parameters, such as the mass, charge, and angular momentum. Once you specify these 3 parameters, the solution is unique. So one is really led to really see what is really responsible for the multiplicity of this black hole entropy. And answering this question is really fundamental for our knowledge of quantum gravity. So really studying black hole entropy is very important for our purposes. And this is what this talk will be about, quantum correction to black hole entropy. So first of all, so as I was mentioning in the title is near extremal. First of all, what is an extremal black hole? So in general relativity, you take in general like a black hole solution. This is specified, as I said, by some parameters, but the existence of a black hole horizon imposes some bounds on the parameters that appear in your solution. So in particular, the black hole like a rotating black hole cannot spin very fast. I mean, it can spin fast, but it's bounded by the mass squared. And also the charge that it possesses is bounded, like, again, by the mass. And the violation of this bound results in a naked singularity. So there are configurations that indeed saturate this bound, and they are called extremal black holes. So extremal black holes are the ones for which this is is an equality. And so indeed, so for these black holes, they are very special because they are indeed, they are stable in general because they have 0 temperature, so they do not radiate. But despite having 0 temperature, the area of the event horizon is finite. It's finite and no 0. And in general, once you have an extremal black hole, the 2 or more horizons coincide, as you will see. Also, these states, these black holes, poses a bit of a conundrum because indeed they have a huge degeneracy of ground states at temperature equals 0. But however, like if you don't have, for instance, supersymmetry, there is an absence of symmetry protecting this huge degeneracy. So one might think that maybe quantum correction can actually lift this degeneracy. And this is something that indeed will be one of the aim of our talk. So also for extremal black holes, something else is very powerful is that indeed there is a symmetry announcement nearby the horizon. So the geometry near the horizon, so-called the near horizon geometry, develops a throat which contains, for instance, ADS2. If we see, for instance, the Reissner-Nostrom like asymptotically flat space, if you take to extremality, the near horizon geometry is ADS2 times S2. And this also happens, for instance, if you have rotation. So indeed, there is some non-trivial vibration over the sphere coordinates of ADS2, but in general, the structure is the same. It also happens in spaces when you have a cosmological constant, for instance, a negative cosmological constant, and also when you have a positive cosmological constant. Although, for these like black holes, for the Sitter black holes, other possibilities arise. And this is something that I will talk to in the second part of the talk. But anyway, let's say as a general case, for extremal black holes, you have this ADS2 throat, which is an infinite throat. And given the fact that you're basically like in the horizon, you're sitting at the bottom of this throat, the asymptotically flat region, like the outside region, seems to be infinitely far away. Thereby, let's say the physics at the throat can be some sort of decoupled from what happens outside. So there is a puzzle, however, when you look at black holes which are close to extremality. And this puzzle was pointed out already back in the 90s by Preskill and collaborators. So indeed, once a black hole becomes very, very cold, the energy available to the black hole scales quadratically with its temperature, according to this law here. However, the typical energy needed, the typical energy of a Hawking that is transported by the Hawking quantum, scales linearly with temperature. So if you plot these two, this is just a heuristic picture for the moment, just to give you an idea of what is the paradox about. So if you plot these two quantities here, you have that the energy available to the black hole is the one in blue, and the energy that is taken away by Hawking quanta is the orange line. So you see that once you are in this region here, once at a temperature which is below this coordinate here, you have that the energy needed to emit one Hawking quanta is bigger than the energy available to a black hole. So in general, indeed, so what the black hole has is not sufficient for the emission of a single Hawking quanta. And so also at this point here, the temperature fluctuation become very large. So the specific heat of the black hole becomes of order 1. And indeed, you cannot trust the classical thermodynamics anymore. And the fluctuations are very, very large. You need something to improve your picture. So a picture, let's say so you need to take into account at that point some quantum correction that in general might alter the picture quite a lot. As it was shown from lessons from Iliescu Turiace and also from other collaborators like Matt Heidemann and also Tao in 20. In general, you say that for charged black holes, you can compute actually this quantum correction by making use of some two-dimensional models, which are obtained upon reduction of the Einstein-Maxwell action or the supergravity action. And indeed, these two-dimensional models are such that indeed you have computational control and quantum effects can be understood and can be computed. So this gentleman here show that indeed if you take into account quantum correction, the energy available to the black hole is raised in this way, in such a way that the black hole can actually go all the way close to extremality by still being able to emit Hawking quanta. In addition, so this is when you don't have supersymmetry indeed. So in addition, you have that according to their picture, if you have this quantum corrected free energy or indeed energy of the black hole, you see that also the apparent degeneracy of the ground states, so the big entropy that you will have at t equals 0, is washed away by quantum corrections, meaning the entropy of the black hole, the quantum corrected entropy, would go actually to 0 instead of being finite non-zero at temperature equals 0. So it's a drastic change in the picture that seems to be indeed justified by these computations. So these were mostly relating charged black holes, rotating or static. The first example were from static black holes. So in the first part of the talk, we will be interested in the Kerr solution. So the Kerr solution is a black hole solution only with spin, without charge. And it's very important because indeed the black holes which we found in our universe, indeed they are rotating, and they're also rotating very fast close to extremality. So this is something that actually is of astrophysical relevance. So we would like to extrapolate their picture to see whether it is wrong or it works also in the rotating case. So some seminal work by Alejandra and Victor Godet, and also by Joao Simon and Boyang Yu, show that indeed also in the extremal Kerr solution, in the near extremal Kerr solution, there is a JT gravity sector. So the same, let's say, mechanism that worked, let's say, the same physics that was in place for Iliescu in the charge case should be in place also for Kerr. But this is something that we have to really show. And we decided to show this by the so-called renormalization of the zero modes. So the aim for now will be to really see whether the picture is the same in Kerr. And so we're going to compute the quantum correction to the black hole entropy for Kerr, and for our other classes of black holes, for instance, the Sitter black holes. And we're going to find that indeed for this picture, you have that the quantum corrections for Kerr lead to the fact that you don't have ground state degeneracy. So the macroscopic entropy that you have at temperature equals 0 is actually washed away. While if you have supersymmetry, indeed, you have a picture similar to the one that Mukund showed before. You have a delta function at the origin, followed by a mass gap, and then a continuous density of states. But for the Kerr solution without supersymmetry, you have this picture, which is very much changed with respect to our expectations. Yes.
In order to extrapolate this, it's a question that I want to know your opinion, because so you're computing quantum corrections.
Yes.
In order to go to low enough mass above extremality, you would need to argue that the result is, say, one loop exact, or which in this case it is not, I imagine, for Kerr.
Probably not.
So then what you know is the beginning of this change of the curve, that the quantum effects are becoming important.
Yes.
And that they are going in the direction of going to 0. But can you argue that there's no ground state degeneracy with
so for
the degeneracy at low energies above extremality, it's decreasing.
Exactly. So we will not be able to trust our computation all the way up to temperature equals 0. Also for other reasons, because there might be also wormholes and some others, so very close. But also
before you get to the wormholes, those are exponentially small scales away from
those. Yes, but also like around here, there is also like super radiance kicks in, so it's also some.
Even without super radiance,
okay.
I think that because super radiance, that's a different matter. But
yes,
your calculations are at one loop.
My computations are at one loop.
Not, there can be higher loops, not
yes.
exponentially small, but
yes,
there can be higher loops, and you don't have that much control over those.
Yes, in 4D, yes. What I can say in that regard is that the result of Iliesio and Turiashi that make use of the 2D geometry, that should be one loop, and the one loop answer is the full answer.
When it's JT in ADS2, yes.
Yes. So if you will need to.
But for Kerr, you don't really get ADS2.
For Kerr, you will need to reduce your theory to some sort of like 2D and then work for that. This we didn't do. So for the moment, we just worked in 4D and then computed this.
I'm just concerned about the claim. How much can you claim about scales which are close to
here, for instance?
Mass, not exponentially close.
No, here, like not here, but
yes,
here.
Yes. Can you claim? You see, as I said, you can say that it's going down, but you don't have control over this in the first correction.
Yeah, we will need to figure out a model, like a 2D model, in which the answer is exact.
And then claim that the model preserves physics.
Yes, claims that the model is the same as the physics of Kerr. That we should. That's what you should, and give the same result as we got in 4D.
Okay, maybe we can discuss more later.
So so for now, let me just put a disclaimer then and say, okay, this is what seems to come out of our computation of the one loop determinant in the gravitational path integral in the near horizon geometry. That's what you get. Of course, I will discuss later what are the range of validity just from this computation of the one loop. Then, of course, there are also subtlety related to the fact that, yes, in 4D, you don't know, and most likely the answer that you get in 4D is not one loop exact, as you were mentioning. But the ones that were found by Iliesio and Turiashi, making use of a 2D answer, are all there is. So there are some, let's say, some intuition or indication that we are going in the right direction. But okay, there are some subtleties, and I can come back to this point later on once I show the answer.
You can reduce Kerr to a 3D.
Yes, and get some sort of warped ADS3, something like that. Okay. If you want, we can talk about it later, but for sure, So all I'm saying is that we are going to show some computation. This computation might not be the full answer. And then we are open to discussion. So as I was saying before, since we have this geometry which contains an ADS2 factor, like fiber or not, but so yeah, this is an infinitely long throat, which in general, which justifies our assumption to work really like for the fact that indeed the horizon physics decouple for what happens like outside. So what we're going to do is to make use of the throat geometry. And so indeed, we are going to assume that the relevant part of the Hilbert space for the black hole can be captured by the dynamics in the throat. And we're going to compute the gravitational path integral in a saddle point approximation. So indeed, we're going to expand around a metric that will be the metric of the near extremal Kerr geometry. This will be G bar. And then we are going to consider fluctuation, and we're going to compute the one-loop determinant. So indeed, the saddle point and the three-level answer, let's say, reproduce the black hole entropy. The first correction then comes from integrating the quantum fluctuations, as I said. And there are some subtleties that were pointed out already by Sen. So indeed, there are divergences because there are some zero modes appearing in the computation of the one-loop determinant. So in general, schematically, what you have is that if you compute, like when you have to compute a one-loop determinant, you have to compute a functional determinant. And schematically, you have to do a bunch of Gaussian integrals. And in general, if you have a zero mode, so these are the lambda is the eigenvalue of the mode appearing in the one-loop determinant. And if lambda goes to 0, then you have a divergence, very schematically. So the same thing, we're gonna find it in the case of a gravitational path integral in the near horizon geometry. So, and the appearance of these zero modes is related to the short-term dynamics in the near horizon of extremal black holes. So it's related, it has an avatar in the JT gravity picture for near extremal black holes. This is something else that I will also elaborate on. And the regulation of the zero modes will be exactly the one responsible for lifting the ground state degeneracy. Okay, so the outline will be this. So I will first describe in detail the computation of these zero modes and this regulation for the Kerr black holes. Then, so I will do two parts. First, Kerr black hole, and then the Sitter black holes. I don't think I will have enough time for anti-de Sitter, but we can discuss it later if you're interested in. So first of all, Kerr black holes. So these are rotating black holes. So the Kerr solution describes a black hole with angular momentum J. And so the metric is this one. It's fairly complicated, but it was written analytically already by Kerr. So this is a black hole solution that, it's a black hole that rotates with horizons located at this coordinate here, inner and outer horizon, plus or minus. The entropy and the temperature are readily computed as the surface gravity and also as the area of the event horizon, the outer event horizon. And in order to achieve the extremal limit, you have to take m squared equals to j. You have to saturate the extremality bound. So once you set m squared equal to j, then you want to zoom in into the horizon. And you do this by performing the following change of coordinates, in which we have introduced a parameter t that will be really like just the temperature. So for t equals 0, making this coordinate change, you get the neck geometry. So near horizon extremal Kerr. So it is a 4-dimensional geometry which has this form, which is the throat geometry that I was talking about. This throat geometry for a rotating black hole. So it has some symmetries. So it has in general, it has in particular SL2R times U1 symmetry, and the generators are this one. So it's really like a highly symmetric configuration. So in order to find then the quantum correction, as I was mentioning, we're gonna use this near horizon geometry. We first analytically continue t into minus I tau, and the regularity at eta equals 0. So let me just go back a bit. So for us, the radial coordinate is eta, t is the time coordinate, and then theta and phi are the usual angular coordinates. So regularity at eta equals 0 requires the fact that we impose the periodicity 2 pi on tau. So the near horizon, so the partition function in the near horizon geometry is given indeed by an integral over a matrix subject to the boundary condition which are dictated. So we are also gonna include the Gibbon-Soking boundary term that enforces the Dirichlet boundary conditions. So the near horizon extremal care is a saddle point solution. So we're going to add the fluctuations on top of that. So we write the metric as the metric of the neck, G bar, plus a fluctuation, H. And we expand the action at quadratic order, obtaining this one, where this is the partition function, the gravitational path integral in the near horizon geometry, has this part here, so the classical part, and then this part here, which involves the fluctuations. And D, the operator D, is a second order differential operator that is computed by expanding this quadratic order. So the path integral computes the functional determinant, so the inverse of the determinant of this operator D. So, and here comes the catch, because indeed, so we choose first a gauge fixing term, and the quadratic operator fluctuation, this D, was computed by Sen, and has this form here. So I omitted some terms that in the Kerr solution, they're just 0. But it obtains, it basically amounts to have this operator here. So it turns out that this operator here supports an infinite family of normalizable zero modes on neck. So if you compute this operator here, you plug in G bar, R bar, the one of the neck, you have that these modes here, which seem quite complicated, but they were found before by Camporesi and Higuchi already in the 90s. If you dress these modes here by this factor here, 1 plus cos theta, something that we have found, indeed, these modes here give 0 if computed on the second order differential operator. So there are modes which are really an infinite family of modes. Notice that also you need to, so they are labeled by an integer n, and n needs to be greater or equal than 1. So the modes with 0, 1, and minus 1, they are excluded from that. So these are modes that indeed are annihilated by the operator D. So these are metric fluctuations, indeed generated by large diffeomorphism, left unfixed by the harmonic gauge. So they are generated by acting on the neck metric with a derivative with this metric here, with this vector field here. So these are indeed diffeomorphism generated by this vector here. You can repackage a bit this mode in a bit more of a physical way. You can just take linear combination of these fields here, extract the dependence of e to the n tau, and you have that indeed the large radius behavior is just this one, meaning that this diffeomorphism here that we found as zero modes, they correspond to boundary time reparametrizations, which are really acts as this. So they're really like what you call in JT gravity the Schwarzschild field. So the modes that I was mentioning before, they need the values -1, 0, and 1 needs to be not taken into account, because indeed, if you take this vector here and you put in -1, 0, or 1, these are really the exact isometries of the neck that I showed you before. So these are just the ones that I put here. So if you compute the Lie derivative of the neck metric via one of its isometries, you get 0. So the zero modes cannot have these values here. So just to recap, so the zero modes are metric perturbations generated by large diffeomorphism that are fixed by this harmonic gauge. They are parametrized by dfs1 mod SL2R. So again, these things are not included. And these modes, they cost no action, but they have infinite volume. So they cause divergences in your path integral. So we really need to regulate them. So how do we decide to regulate them? Well, these people here had a very smart idea to regulate them by adding a bit of temperature in your metric. I'm not saying it's the only way in which you can regulate, but it's something that will lead to physical results.
What other ways of regulating it that would be physically meaningful would there be? And because I hear sometimes people say there's other possible ways of regulating them, but I never get a straight answer to it.
Yeah, okay. No, this is just a disclaimer that I made to cover it up. I mean, I think it's probably the most natural way to regulate, given the fact that you have an infinite throat and then you're kind of almost capping it off.
Is there a natural way of regulating them? I mean, there's extremely unnatural, but anything that would make sense
beside this.
When we have zero modes, we always have to introduce some
cutoff, yeah, or something like regulator, yes.
Very often there's a very natural one.
Yeah, volume or something like that, yes.
I don't know whether in this case there might be another interesting regulator.
I don't know, maybe not in asymptotically, maybe not in asymptotically flat, maybe in some other, maybe I don't know, if you find some other black holes in anti-de Sitter or something, you might find something else.
Yeah,
but it might be.
There's another physical regulator, then maybe we can get other physical consequences.
Yes, maybe, but.
If there's some other physical regulator, I would like to know, because that would be. I don't think there's any other. Yeah. I mean, having able to projects could give you some other kind of benefit, right? These are zero modes only when you consider Einstein's gravity. That's if you had any other terms, it could regulate this zero modes.
Mm-hmm.
No regulatory time.
But sorry, in principle, aren't you supposed to not to regulate the integrator over a possible solution? So this is telling you that it's not a single surface, but there is a family of surfaces. And in principle, you are supposed to integrate over all of them. Now, whether this is possible or not, I don't know, but this is what is understanding.
These are not moduli. Yeah. These are not moduli like usual because they're coming from large zero. So if you think about the analogy in higher dimensions like ADS3, these are the analogs of the Brown-Hanover modes in ADS3, and you wouldn't sum over all the Brown-Hanover sectors there because they're not modular.
From the point of view of the saddle point.
Yes, there are fluctuations along the saddle point generated by vector fields that are not normalizable. So they're not strictly, if they were normalizable vector fields, you would just quotient them out because they're trivial isomorphisms. So they're part of the same, they're just different representatives of the same gauge orbit. But here they're not even that. You should treat them separately. I don't think collective coordinates of integrating one moduli into it.
Okay, but it's a good point, so maybe we can discuss. Yeah, feel free to interject at any time. So the procedure, like taken from these guys that first put them in place, is to really regulate these modes by going a bit out of extremality. So by adding the linear term in temperature to the near horizon geometry. So indeed, instead of considering only the neck geometry, you consider the first term that arises in the decoupling limit. So let me just go back. Sorry for going back and forth, but if you remember, I was performing this diffeomorphism to get this. Now we get this, but also we retain the first order in temperature, and we get a metric which is overall quite complicated, but still manageable. You just write it down. And then you compute the correction to the eigenvalues. So the eigenvalues that we're interested in were the ones that were zero, so the zero mode, so its eigenvalue is zero. You compute the correction via perturbation theory. If you compute, if you indeed via perturbation theory, where indeed your t is the perturbation parameter. So this means that just as you do, for instance, quantum mechanics with the Lippmann-Schwinger formula, so you have to consider this indeed this modification of the operator D. This is the second order differential operator on the neck, and this is the modification that is that arises because of the temperature. These are the modified eigen modes. These are their eigenvalue correction, and also again these are the eigenmodes. So what we are after delta lambda n, which is the correction to the eigenvalue 0. H0 are indeed the extremal eigenfunctions with eigenvalue lambda 0. So if you're interested into this quantity here, you just you don't need to know this delta Hn. You just take the inner product, and using orthonormality, you get this formula here that gives you the delta lambda n. And once you know this, indeed, then you can compute the correction to your partition function. So computing this one is a bit of a, we did it brute force. And yeah, it takes quite a bit of Mathematica, but it's pretty doable. After integration, you get that indeed, like the expression for delta lambda n, I mean, initially it's super big, but then it simplifies really a lot to this term here, which is of course linear in t, because by definition, but also it's linear in n. And also to remember that n, we need to exclude the values n equals -1, 0, and 1. So the correction to the partition function contains this one, so contains indeed the corrected eigenvalue. So if you use this formula here and you perform zeta function regularization, you get that the modification of the partition function, like indeed contains a 3/2 log t term. So if you put now things all together, you have that the black hole partition function has this overall factor, like the t to the 3/2, which depends indeed, which is given by the fact that you have a 3/2 log t correction. And then this is just the semi-classical part, where it says that the entropy scales linearly with temperature. So this is the formula that you get when you put all together. In particular, this means if you take the Laplace transform of this, you get the density of states in function of the energy. And as the energy goes to 0, you have that you don't have any exponential ground state degeneracy or thermodynamic mass gap. So it means that if you plot this, the density of states for the Kerr solution once the energy is 0, so close to t equals 0, the density of states goes to 0. So it means that you don't have this macroscopic entropy that you thought you had in the classical computation. So as we were mentioning already at the beginning, there are some indeed there is some range of validity to this formula here. So even disregarding the fact that the answer might not be one loop exact, as Roberto was pointed out. So the approximation is still, it's not valid when the temperature is too small, meaning it's exponential in black hole temperature. So I cannot really go all the way super close to t equals 0, because at this point, indeed, like other saddles, or you have non-perturbative effects such as wormhole, began competing. So we use indeed the saddle point approximation, but at this case, there are other saddles. So you cannot go too low in temperature, but you can also go really too far up in temperature, because if the temperature is too big, then the linear term that you find here begins competing with the leading S0 term. So indeed, the correction becomes as large as the neck metric on the other side. So that's something that you have a range of validity for this formula. So some subtleties that so far we have considered only tensor modes for the graviton fields, but of course the zero eigenvalue, like the zero modes in the Lichner-Horowitz operator, in this operator D, usually are associated with symmetry which are not removed by gauge fixing. So you have other symmetries in your solution. In particular, in addition to tensor modes, there are vector modes that arise from isometries of in case you have a static black hole, you have isometries of S2, so SO3. In case of a rotating black hole, you have one residual isometry. So you still have rotation like a U1, which is a d phi killing field. So in general, Sen gave a proposal for this residual rotational zero mode, which is this one. However, and let me also mention that these rotation zero modes, they are associated with fluctuations in the angular velocity. So they are really depending on the choice of ensemble. You can choose your ensemble to have a fixed angular momentum, fixed angular velocity, and so on. So the 3/2 log t correction is universal. These ones are ensemble dependent. So in general, what you have is that Sen's proposal for the vector zero modes is actually seem not to be working. So like Mukund and collaborators also found, but we also verified that indeed the guess made by Sen is not a zero mode of the operator D that arise in the neck, due to the fact that it doesn't satisfy the transverse traceless gauge condition. And this was something a bit puzzling, but Mukund and collaborator also show that indeed, like this is something that you can understand from the fact that indeed, so this is not a zero mode for indeed, so this is not a zero mode for the like a rotational zero mode. However, there are ghost zero modes that are indeed take the place of this rotational mode. Mukund, if you have some observation, just if you want to add some more. Okay, fine. Okay, so further developments that I feel like we should mention, since we can also have a bit of a discussion later. So indeed, the zero modes extend to modes defined in the full geometry. And it is nice to see that, like in the extremal limits, they become localized near the horizon. So indeed, there is some physical way to extend these modes all the way to the full geometry. And also the Tri-Half-Lofty correction can be retrieved by the DHS formula by using quasi-normal modes for BTZ. And also Giulio and Alessandro and collaborators also found this for Kerr beautifully. And again, one thing that we should be really careful of is that we know that the extremal Kerr solution suffers from superradiance. So if you scatter scalar wave out of the Kerr black hole, they get out, which are amplified. So this is an instability, this signals an instability for the Kerr black hole. And so far we have neglected this effect, and in general, it will kick in for sure the same order as the quantum effect that I showed you before. So we need to be very, we will need to incorporate this effect.
That's not in the Schwarzschild signal, right? You have to couple
no.
Some other geometrical mode to the Schwarzschild, and that's when you.
Yes, exactly. Yes, yes. So, okay, if there are no other questions so far, I'm gonna go to the second part of the talk, which involve de Sitter black holes. Okay, so the motivation for doing that is that indeed, indeed, the Sitter spacetime is relevant indeed for cosmological purposes, and we wanted to really see how the environment in which a black hole lives really modifies the horizon dynamics. And there are some differences and analogies between black holes which live in the Sitter, anti-Sitter, and Minkowski space. So before the Kerr solution that I showed before lives in Minkowski space. Now for the Sitter black holes, there is something like a bit different. So the Sitter black holes are characterized by the presence of a cosmological horizon that bounds the black hole in size. So indeed, a black hole cannot be too big. And the cosmological horizon itself can also be treated as a thermal entity, as its own thermodynamics. And indeed, the thermodynamics of the cosmological horizon was really indeed studied first by Gibbons and Hawking, which indeed show that there is a minus sign in the laws of thermodynamics for the cosmological horizon. Also, in all this talk, I'll put here a footnote, but indeed, so there are also various subtleties about the fact that for this, the Sitter black holes, like in general, the temperatures of the cosmological horizon and the other horizon, they're not the same. So in general, this configuration, they're not in thermodynamics equilibrium. And also the fact that you have a horizon, in general, you don't have an asymptotic region where like a conserved quantity can be computed. So there are a bit of subtlety that I'm sweeping under the rug. But okay, given this, so we can study de Sitter black holes, and we choose to study charged de Sitter black holes in just the cosmological Einstein-Maxwell theory, so Einstein-Maxwell lambda. So the black hole solutions that arise, they are the Rystrom-Nordstrom de Sitter black holes. They are spherically symmetric configurations, which have electric charge in this case. The warp factor is this one, and it can be rewritten in this way. So it can be rewritten as a quartic order polynomial over R squared. And indeed, so these two roots here pertain to the fact that you have a de Sitter black hole. These two ones, the outer and the inner horizon, they are the ones that pertain to asymptotically flat. So the addition of cosmological constant brings out two more roots. So the ones that I call RC2 will always be negative. So it will not play any role in our thermodynamics, but RC will be really relevant. So the positive roots that I indicated here will be, so R plus will be the outer horizon, R minus is the inner horizon, and RC will be the cosmological horizon. So if you remember from before, I defined the extremal solution as a solution in which two of the horizons coincide. And in this case, you have two or more horizons that can coincide. So indeed, there are three different extremal limits. Let me first mention that physical solutions, so solutions with horizons, are the ones that are here in gray. They have in general, these are near, like non-extremal black holes. The ones that are here in the region which is white, instead they're naked singularities. So this diagram here is called the shark fin because of its shape. So the shark fin is bounded by the cold black hole. So the cold black holes are this dashed line here, arise when the inner horizon is equal to the outer horizon, so R plus equals R minus. You have then another solution, which is called the Nari solution. It happens where the outer black hole horizon is equal to the cosmological horizon, coincides. And this is the other part here of the shark fin. And you have just one point, so it's just one point in parameter space. It's called the ultra cold solution, in which all the three horizons coincide, and is the star at this point of the fin. So what we did in various different papers with my collaborator is that we have analyzed different excitations above these extremal solutions. So indeed, the reduction on the sphere gives a model like generalization of JT gravity models. And what we have done is compute the logarithmic, the log T corrections to the black hole entropy in these three cases. And also, let me mention before going on, that the cold black hole is the one that is most similar to the black hole that you have in asymptotically flat, because its near horizon geometry is ADS2 times S2. Nariai solution has a near horizon geometry DS2 times S2. The ultra cold solution is Minkowski 2 times S2. So if you have to consider the near horizon geometries, there are three different cases. So, okay, so the first results that we got here is that we have analyzed indeed the fluctuations above extremality, like by using indeed the reduction on S2. So you perform these, you impose these ansatz here, you reduce it to 2 dimensions. You get the following action here, and linearizing this action around the IR value, which is ADS2 times S2, you get like de Sitter JT gravity. And in the case where you have the ultra cold solution, you have a model of CG HS hat model, so which is dilaton gravity in asymptotically flat two-dimensional space. So what is known about this model where people actually have used them? Well, yes, indeed. So people like already in 19th computed some quantum corrections in this model, but they have used a slightly different object, which is the wave function of the universe. So they computed some quantum correction of the wave function of the universe in these models of de Sitter JT gravity. So something was already done at the level of quantum corrections. What we do instead, we don't consider this object, which is like a, indeed like, this comes from the partition function of particular complex geometry. We don't do that. We choose to work as we did for the neck geometry. We choose to work with the path integral in the near horizon geometry of these black holes. So ADS2 times S2, DS2 times S2, Minkowski 2 times S2. So we need to take into account then contribution from the tensor modes, the one that gave the 3 half log T corrections, the vector modes, which are the one due to the rotational isometries, and also photon zero modes, because indeed you have also a gauge symmetry, and there are these modes that are also playing in the game. So for the first solution here, so these are the cold black holes. So the first case, we have that R plus equals R minus equals R0. And you also have the constraint that this R0 needs to be smaller than a specific value dictated from the cosmological constant. These are also the parameters in your solution. So you can zoom in into the horizon, and you get indeed the ADS2 times S2 geometry. Also, you can compute the response coefficient of your solution. Indeed, they scale as this. The mass scales quadratically with temperature. The entropy is linear in temperature. And the mass gap, this coefficient here, is positive. So this solution here has positive specific heat. So in computing the quantum correction, then we have to do like we did before. We first rotated, like we rotated our solution, and we keep the first ordering temperature in the decoupling limit, both in the metric and in the gauge field. And again, using the perturbation theory, you compute the eigenvalue correction that gives this formula here. Again, you have zero modes, which are the same one as Camporese and Higuchi found. You have to take out the modes which are n equals 0, -1, and 1, and you get this formula here. So as before, for the Kerr solution, by using zeta function regularization, you have a contribution of 3 half log T from the tensor modes. And also you have to include contributions from other modes, which are already computed. So you have 3 half log T from the tensor modes, 3 half log T from the rotational zero modes, because you have SO3 isometry, so there are 3 modes, each one of them is 1/2. And also you have a gauge field mode, which is like, it comes with a 1/2 in front of it, like as the result. So,
it's a question that I
yes.
asked you and your collaborators a few months ago. So when you're slightly away from extremality, you're not in the really cold limit the instanton in the sitter is not well defined, or it's not completely regular.
Because you cannot balance the singularities, yes.
The difference is very small. I think
yes,
there
yes.
could be a way out, but I would like to see.
Yes, so it is indeed something that, so for now so it is true. Well, what Riccardo is saying is that given that these configurations have a different temperature at the cosmological horizon and at the outer horizon, you will have a conical deficit at one of the 2 points. So your solution will have some sort of like a conical deficit at some point. So this is for what concerns the full solution. It is true, yes. We thought that in one way we kind of don't address this problem by just considering the horizon geometry. Of course, if you had to embed this into a full geometry, the full geometry will have this conical deficit, and it's something that we would need to think about. For the moment, we bypass this thing, but it's not bypassing. But I mean, like, we just consider the horizon geometry.
Have updates on this question?
No, unfortunately not. But we still think about it. But okay, so that's what I was mentioning also by saying that these solutions are indeed something they're systems which are not in equilibrium, because indeed you have this cosmological horizon which already has a temperature. So situation is a bit different from asymptotically flat black holes, but nevertheless we proceeded and see what we got. So summing up all the contribution, you have 3/2, 3/2, 1/2. You have 7/2 log T correction if you sum all these modes for the cold black hole. So let me mention that there was also another paper by Maulik, Mitra, Mukherjee, and Ray that also found the tensor mode correction. In addition to that, we also computed the contribution from other modes. And also we show that you don't have any ghost zero modes. And also let me again stress the fact that we computed also the contribution from other modes. In particular, the gauge mode contribution is non-zero. In asymptotically flat, instead it is zero. So it's something that happens a bit differently with respect to what is in Minkowski. So now let's pass to Nariai configuration, which is a bit like it adds a bit more problems. So first of all, if you do the same procedure as you did for the cold, you get ds2 times s2. And if you consider the expansion around extremality, you have that the energy of the black hole has this formula here, but the mass gap is negative. So this means that this solution has negative specific heat. So it's already by itself is unstable. So something that as a ground state is not quite what you would like to work with. Nevertheless, we proceeded and see what we got to see if there exists some other pathology signal in this. So we again rotated and kept the first correction in the near horizon geometry and computed the correction to the modes. So it turns out that indeed there are some pathologies that come up because the tensor modes have negative eigenvalue correction. So this is something that instead of giving a Gaussian, like in your path integral, let's say, you will have something which diverges, so which is really not good. Vector modes have a negative norm, and also for a specific range of charge and lambda, they have a negative contribution to the correction. So again, delta lambda can be smaller than 0. This is really something that depends whether you are above or below the lukewarm line. So okay, for the experts, maybe I see Roberto nodding, but I can explain a bit more. But in general, you also have pathologies also for the vector modes. And the gauge field modes also negative norm, but positive correction. So you have either negative norm states or also negative corrections, which both signal pathology, and in particular a divergence to your path integral. One can try to circumvent this problem or try to fix this problem by consider a complexified black hole solution, like let's say to do some sort of analytic continuation in your geometry. So you can actually consider this geometry here, which is a solution to the equations of motion. You have to do some sort of like complexify the radius, also take some parameters such as the mass, the charge to be complex. Anyway, you get this near horizon geometry, which has an overall minus sign on top of it. And it is surprisingly a solution to the Einstein's equation with positive cosmological constant. It cures some of the pathologies, but not all of them. So certain modes have a positive norm and positive correction. However, gauge field modes have negative norm and negative correction. So it seems that we Narii always have something that that seemed to be pathological. So indeed, so if the correction to the eigenvalues is negative, we don't have a convergent Gaussian in our path integral. So in general, probably it's something that somehow we could have expected. So negative eigenvalues in a gravitational path integral are really not new. So if the conformal mode, for instance, also has negative contribution to the path integral, and in particular also if the solution has negative specific heat, is something that we could have thought it would have happened. So in general, what you can do is to change the contour of integration, like flip it into the imaginary direction. It gives a finite answer, but you have also some complex quantity. So
isn't this the calculation that recently Turiachi they find that it's
yes, I think yes. In the next slide, I mean, I will be talking about this. I mean, not quite what you get, but for sure they have a paper also on that. So what we found so far is that yes, for the Narii solution, given that it's a background which is already unstable and so on, there are indeed pathologies. So if you compute the correct quantum corrections to the path integral in the way we did, you find that something goes wrong. And so indeed, compared to the first studies that were found by Maldacena, Turiaci and Young, and Kotler, Jensen, Maloney, they worked in 2 dimensions. Of course, they were computing something else, the wave function of the universe stuff. But the new feature in 4D that we added is that we could see also these vector modes and the gauge modes. So, okay, so this is a summary of all the correction that we found. Somehow it seems that the cold is okay. But the Narii, so we also included the Schwarzschild Narii, which doesn't have the ultra cold point. But wherever you, even if you switch off the charges or if you complexify your metric, it seems that there are still there's still some pathology. So somehow we cannot really make sense of that. So there were also some other nice literature that studied this problem that actually came out quite a bit, quite at the same time as our paper came out. Well, first of all, the paper by Maulik and collaborators that also computed the tensor modes. But also Turiaci and Wu had a beautiful paper computed indeed the quantum corrections to the wave function on S1 times S2. And in this case, they also consider some sort of they also consider a different geometry. So it's not exactly what we do. So we computed the path integral correction in the new horizon geometry. They computed the partition function on a geometry which is asymptotically S1 times S2. Like it has this boundary. So this is this S1 times S2 boundary. And in general, they found that these corrections, so the Schwarzian corrections that they found, render the norm of the wave function finite. So for them, it seems that if you compute the wave function of the universe, you get something that makes sense. It's, of course, a different procedure. And recently, if maybe at some point in the discussion we want to talk about it, it seems that Giulio and Alessandro computed the corrections, the quantum corrections to the near horizon geometry of yes. Sorry, I don't. Okay, and Paolo Arnaudo. Okay, yes. Sorry for not. And computed, okay, the corrections via some sort of DHS formula via the quasi-normal modes, and it seems that also there the Narii doesn't give the 3/2 log T corrections, and we can talk about it more. Maybe there is no. I think it's there's no confluent solution to the equations to find quasi-normal modes. So somehow it seems that it's these 3/2 log T corrections in Narii seem that they're not quite showing up. And just as a last, let me mention that indeed, the Narii geometry also, if you take into account more general quantum effects, you have some very weird features. You have some sort of anti-evaporation. So there are some sort of weird stability of the Narii geometry. And these people actually show that indeed you have to take into account some other quantum effects, and this geometry can actually anti-evaporate and go back to the extremal solution. So this quantum effect can alter again your picture, and it needs to be also taken into account, but something that we didn't do. So, okay, in the last maybe 10 or 5 minutes, I can just go on to report a bit on the ultra cold configuration. So I have five minutes. Okay, so for this solution here, as you might remember, this is the tip of the shark fin. It's where the two lines, the cold and the Nariai, intersect. So it is characterized by having three coincident roots. So the work factor has a triple root at this thing here, and it's just one specific point in the phase space, which is in this one. So the new horizon geometry, you need to also perform quite a funny scaling limit for the new horizon geometry, which is this one. It scales like where the parameters lambda scales as lambda to the 3/2. So if you perform this decoupling parameter, the new horizon geometry that you have is Minkowski 2 times S2. Remember that the other two were DS2 and also anti-de-Sitter 2. This one you have Minkowski. So this is something that is still a work in progress. So it just seems that this configuration is a bit problematic because we don't find really actually well-defined zero modes. But let me take a step back. So first of all, in this work in progress that we're gonna hopefully continue, we found indeed a way to really fix the chemical potential and to achieve, like to consider the next order term in the decoupling limit. And we had to take a particular displacement of the horizon to get that. But in general, we can also cast the near extremal solution into this form here, where in this case, the temperature scales quadratically in the decoupling parameter, while if you have the cold, this was not holding anymore. This temperature was linear in the decoupling parameter, was actually the decoupling parameter, as you remember, one of the first slides. But okay, so for the ultra cold solution for this point here, it seems that first of all, we cannot construct diffeomorphism, so this vector Xi that had the role of the Schwarzian before, that mimics the asymptotic symmetry group of two-dimensional flat spacetime, so which is some sort of BMS group associated with Minkowski 2. So it seems that if you work in the transverse traceless gauge, you have problems. You cannot retrieve the full BMS2, like all the generators of BMS2. And also another issue is that indeed, if you try to solve with the transverse traceless, you find some modes that not all of what you would like, but also the modes that you find, they have IR and also an UV divergence. So they're not normalizable. They have infinite norm. So what we are trying to do now is that we are releasing the transverse traceless gauge, which is notoriously, apparently, if you talk to people knowing flat holography, is problematic for BMS, for instance. So we are deciding to work into another gauge, and we found some modes which are indeed reproducing the full algebra. However, these modes present either IR or UV divergences. So we need to figure out if this is something that makes sense or not. We probably kind of expected an IR divergence, as all you have in asymptotically flat, but also UV, I mean, I don't know. It just seems that something goes a bit wrong for the ultra cold solution. But so what we have now is that we have these modes, even if they are UR and IR and UV divergent in their norm. We are trying to see if they're actually zero modes of the operator. And so we borrowed the result from this paper here. We have the Lichnerowitz operator in axial gauge, which is this one. And we are trying to see whether these are zero modes or not. So of course, we are open to suggestions whether maybe there is a proof of principle that normalizable modes cannot exist in two-dimensional Minkowski space. And they were there because they were known already in ADS2 from Camporese and Higuchi, but in Minkowski 2, it could be that they really cannot exist, these modes. However, so the results by all of you guys, all the three of you guys, show that for the ultra cold solution, there is a 3/2 log T correction. So somehow this gives me a bit hope that the modes that we found here, they're exactly the one that would be responsible for the 3/2 log T correction. But it's something that I cannot say. I mean, I'm really puzzled, and maybe there is a reason why we don't find good modes. This is something that we need to really figure out. But it would be nice to discuss a bit more on this point. Okay, before, just one slide, yeah, the result that this gentleman found was for the ultra cold Kerr de Sitter, also with my former master student Francesca, which is now a PhD student in Ghent. We have analyzed the thermodynamic response near extremality for Kerr de Sitter and Kerr anti de Sitter. And of course, so this will be, let's say, the starting point towards the computation of the corrections that Sabayashi Maulik and collaborators also found already in the ADS case, but the next step would be to try from this metric here to compute the quantum corrections and verify the results of you guys. Okay, then I think I can just skip this part. Okay, so concluding, so I have provided here, I've shown a framework where you can actually compute this correction to near extremal black hole entropy with all the caveats that I told you, and that also that Roberto helped in kind of bring it up. And so the correction that we have now, the procedure that we have now, it seems that like it's responsible for, like predicts lifting of the ground state degeneracy, meaning that indeed like of the extremal non-supersymmetry black holes, such as the Kerr black hole that exists in our universe. So, I mean, I think it's a pretty important, it's a pretty important thing to investigate because it's something that is very, like, that is really something physical that people took a picture of. So it might be nice to really have some more workforce on that. And of course, lots of things still need to be done. So the incorporation of superradiance, first of all, could actually invalidate some of our results. So, so that's very much something that that would be nice to figure out. And also for the de Sitter case, yeah, we have a lot of puzzle because it seems that the Nari solution is plagued by these modes. And also for the ultra cold, as I mentioned, these modes, we don't know if they are proper or not, and it's something that is still work in progress. Okay, it's the end. Thank you.
Questions? Please.
Yeah, I'm going to ask about alpha cold case.
Mm-hmm.
My instinct would have been that alpha cold case doesn't need to be Gaussian super rather Lipschitz geometry. This is what I would expect by coalescing fields. And is this what I've asked you this question before, but I don't see why it's not.
So
no, I mean there's a very natural way you have a function with singles.
Yes. I see your point.
Yeah.
And if you do the scaling, which was done already in Robert's paper, you get a Lipschitz geometry.
Yeah, I see the point,
but I thought that
it's actually CGHS, which is Minkowski.
no, I think, yeah, you're mentioning already the near horizon geometry, right? Just at the level of the near horizon geometry, you think it should be Lipschitz and
yeah, I mean, if I do the same thing I can do for horizon or any other
so
coalescing horizons, I will get some Lipschitz. There's a scaling solution, let me put it this way. There's a scaling solution that's valid, and then the scaling solution is valid in the horizon, and it solves Einstein equation on the node.
Okay. So what I can say is that if you, so I cheated a bit when I was showing you the decoupling limit in the ultra cold. So this one, the way Romans or people like okay, I can okay, I don't remember I don't remember the name, but I can point out the paper is that they first a bit displace the horizons and then they take a decoupling limit and they get Minkowski 2 times S2. Could be that it's the one, it's a different decoupling limit with respect to the one that you were mentioning. Could be that there exist different decoupling limits that land you into different geometries. But I thought that, I mean, for sure, I mean, okay, this was a bit schematic, but for sure I did their computation themselves. They displaced a bit the horizon and they take the decoupling limit. That lands you on Minkowski 2. But I don't know if it's a procedure that you have in mind. Well, the geometry, yeah, the geometry itself is still, okay, you mean the total geometry Minkowski 2 times S2, yes, still has curvature, right? Because it needs to solve the Einstein's equation with positive cosmological constant. But you say there should be on Minkowski 2.
Minkowski times S2 will not solve Einstein's equation for this. That's what it is.
So, but
If you do it with charge, then it's clear that it's the ultra-cold limit cannot be reduced.
you mean?
If you're doing it with charge, spherically symmetric.
Yes.
Everything is going to be just different contributions to the effective two-dimensional cosmological constant. I don't think.
So what we so for instance, once we
because with rotation things can be a little more.
Yeah. So what? Let me go back. So we have verified that Minkowski-2 is a solution of the 2D reduced theory. So
Okay. Yeah. Maybe. Yeah.
so if that, I mean, if all the solutions of the 4D are also solution of this satisfies the equation, and then it should uplift to a solution.
In case it's a question that's well defined.
I mean,
yes.
if you plug in the values for, of course, you have a specific. The ultra cold point is a specific one that arises just for a specific choice of parameters. Like you have to impose. Okay, sorry, I'm going back and forth. Sorry, but you need to impose this one. So you need to perfectly balance them. But if you impose this, the solution that you get in 2D, it just solves the equation. So, but yeah, but maybe we can do it on the blackboard and then see. But that solved our equation, I think. So it seems, I don't know, at least it seems that from the papers that we've seen, for sure, they seem to take it really for granted. And I redid the decoupling limit and I checked the 2D action. So, but we can literally try to do it on the blackboard and then, or Mathematica, and see whether we can get. But my feeling is that this is for sure an option. But then, if it's defined as much as you like or not, that's up for debate. But
you see that CDHS, and then you want to find zero modes here that would reproduce a log T.
In principle, that's what we would like to find. In principle, that's something that, yeah, it seems that the ultra-cold solution also has the 3/2 log T. So we are trying to just figure out if, so far we have modes which need both IR cutoff and a UV. Some of them, they need a UV cutoff. Some of them, they need a IR. I don't know if it's something that it's proper to consider, but this is what we could construct so far. But yeah.
More questions? Okay, if not, we thank again Chiara for we reconvene at 2:30.